Um, yeah. So feel free. Okay, so I guess we can just like start off by just like walking why it was created, and then maybe go a little bit then into how it works, and why some of the design decisions were made. And then anyone, please like butt in and like ask questions as we go along, because I prefer that instead of like, I don't like people getting lost in the middle and then not knowing what's going on for the rest of the time. So yeah, okay. So Tendermint consensus. Essentially, there's this dude. His name's Jaquan. Back in like 2014, he was like really interested into like cryptocurrencies, and he got into it. As I bet a lot of people do, they're like trading and whatnot. But then, Jay's a little bit of like a little hippie dude kind of thing, and so he really cared a lot about like the environmental impact stuff around like Bitcoin, and he kind of just like saw and predicted like, okay, this proof of work thing is not environmentally sustainable. It literally makes zero sense that we reward people for wasting energy, when in reality it would be nicer if we had a system that rewards like capture of potential energy, not wastage of energy. Sorry, was that a question? What? No? Okay. Yeah, and so then, the idea was, okay, how about, then there was always this like proof of stake thing that was like kicking around the Bitcoin forums. Sonny King from like Peercoin kind of like was the original person who proposed it back on the Bitcoin forums, and then there were a bunch of like early implementations of proof of stake from, for example, some of the people at like NXT and whatnot. But one thing that happened was a lot of the people who were working on these original attempts at proof of stake were kind of mimicking a lot of the features of like the Nakamoto consensus proof of work. So this whole like longest chain thing where people build on top of the previous block, and then whichever chain is the longest is the correct chain. And then also all the chains that were going around at the time were also suffering from this issue. Like, so I'm talking about the early proof of stake stuff, like Peercoin, NXT, what else? But yeah, these guys, it was all usually they either switch to like some hybrid proof of work, proof of stake, or like they just like said, okay, sure, nothing at stake is fine. So Jay basically did a lot of, he started reading a lot of like the old consensus literature, like the classical BFT literature from like the 80s and 90s, which like, surprisingly a lot of people in the blockchain space hadn't really read and like, looked into. And so he kind of saw, he looked at like DLS and he looked at like PBFT, and he's like, oh, okay, what if we could take some of these more classical BFT consensus mechanisms and apply them to a blockchain context? One of the biggest issues with a lot of why this was never really considered before was, BFT traditionally was usually meant for permissioned settings. And no one really thought of how to use it for a public, decentralized, or open network. And so this is why, like, the whole proof of work stuff came around with Nakamoto consensus. And then, like I said, proof of stake was developed from proof of work. And so what Jay realized is, oh, wait, we could actually use this whole proof of stake thing, the stake weighting, to create a somewhat open system that acts as decide what is the validator set of the Tendermint of a BFT system. And you kind of like, getting to that point where you can use proof of stake to decide, like choose the validators for a BFT system, it kind of had to go through Bitcoin and proof of work as like a necessary stepping stone. Because without Bitcoin and proof of work, I don't think we would have realized that, a digital asset that can have value purely because of the reason that it's decentralized. And so Bitcoin and like the proof of work system had to exist first in order to prove that these things can have value. And then once we learn that these things can have innate value for some reason, then you can actually make the leap and create proof of stake. So, a lot of people think like, so if you talk to a lot of like Bitcoiners, they'll be like, oh, people have been trying like, we've known about classical BFT protocols for like 30 years. Why haven't we seen any decentralized networks based off of them yet? But then in reality, it's like, not really, it was not possible to create these decentralized networks off of BFT protocols until like maybe the last 8 or 9 years after like proof of stake, the idea of proof of stake came about. So yeah, that is sort of a little bit of the history. So Jay, what he started to do was so a couple of people were trying to solve this like nothing at stake problem somewhat simultaneously. I guess a brief run through of what the nothing at stake problem is for anyone who's not too aware. It's the issue that in proof of work, what's nice is if you have a certain amount of hash power and suddenly there's a fork, you have X hash power. You have to choose to divert your X hash power to one fork or the other. You can't really use X hash power on both. You can do half and half, but I don't know why you do that. But in proof of stake, that's not really the case. Let's say there's suddenly a fork, and now you have the same amount of coins on both sides, and there's actually no reason for you to not just keep building on both forks. And if everyone decides to just keep building on both forks, then we're never going to resolve a fork, and we don't come to any sort of consensus on the state of the system. So a couple people were kind of like interested in this problem in a somewhat simultaneous time. I'd say like kind of the three people who were like really like thinking about the problem and came up with like solutions somewhat in parallel were Jay with his Tendermint work, Vitalik Buterin, he was working on a project called Slasher, and then Dominic Williams, he was working on a project called Pebbles, I think it was called back then. And I honestly don't know too much about Pebbles, to be honest, but Slasher was trying to solve. Honestly, all of the solutions kind of had the same concept of like slashing, where you allow forks to be able to know about the other forks, and if you, as a validator, get caught double signing on two different forks, you get slashed on the opposite fork. Yeah, and removed from the validator set. That's kind of really the key. So if you're not talking about like proof of stake, but like just in consensus terms, you get removed from the validator set in that case. And so Vitalik Slasher was kind of still going along this very like Nakamoto consensus-based system, while Jay started looking into especially the DLS and the PBFD consensus protocols, and trying to figure out how to adopt those protocols for the public blockchain setting.
Yeah, can you make a question? So when you say DLS and PBFT, I think so DLS is Dwork, Lynch, Stockmar, right? But what is the difference between those two styles? What do they mean? What is just like a brief overview?
I haven't read DLS. I only know PBFT.
Okay. DLS was sort of just a lot of ideas from DLS were about using like authenticated encryption in order to be able to attribute messages between nodes, between validator nodes, and that was sort of like one of the key things that was gotten from DLS. And then PBFT sort of built on it from DLS. And one of the things that PBFT sort of did, so really what happened was Jay read DLS first, and DLS actually had this like 3-round system, and then Jay started reading about PBFT. I think the original, some of the earlier designs for Tendermint were heavily based off of DLS, and then what PBFT did was it removed one of the rounds. it kind of So PBFT is really more off of a 2-round commit system, and so the proposal isn't a round of commits, right? It's not a round of votes.
Okay.
Like DLS had 3 rounds of votes, I'm pretty sure, and so that was sort of like after we had PBFT later on, after a little bit into designing Tendermint, he's like, oh wait, okay, maybe I can make this actually even better. That's sort of like the main. Honestly, it's really more of a PBFT inspired protocol now at this point. It's just that originally when he first started, it was like DLS based.
Yeah.
That helps answer the question. But yeah, I don't know. DLS is like the hard paper to read. Anyways, so some of them, the main things that Jay was trying to see. So PBFT basically what it does is you have a leader who basically gets to propose blocks or propose values. Back then there were no blocks or anything. This is a modern thing. You propose values, and then the other nodes sort of do a reliable broadcast system to decide on value, whether or not a leader decide on the values that the leader was committing, and then in the scenario where the leader, and so you sort of have the same leader who's constantly the leader, and all the other n-1 validators are just sort of just committing on the blocks. And then you have everyone has this local timeout system where if it gets to a point where the leader goes offline or is Byzantine or you just don't hear from him, then we have a separate mechanism that's designed for view changes. It's a sort of a way of us voting, and this part is pretty partial. It's partially synchronous. The voting mechanism is honestly not that different than the RAF mechanisms for re-election. And so you do the separate mechanism for re-electing a leader. And so Jay was looking at this PBFD stuff, and he noted he wanted 2 things. One, he wanted the primary thing he wanted here was the ability for every round, don't have a fixed. Basically, PBFT, what it's saying is there's one leader and he remains the leader until he fails to be the leader, and then we re-elect. Jay said, what if we can have a system that constantly is rotating the leader in a sort of round-robin fashion? Every validator gets a chance to be the leader. You have a question?
So I had gone through the PBFT paper. I just wondered why does such protocols always starts with a leader, right? Because the questions of the view changes arises because there is a leader in the starting, right?
Uh-huh.
So why do all such protocols start with a leader? Can there be a protocol which doesn't have a leader?
Yes. Yeah. The issue with those is you have more rounds and an n-squared communication complexity. So you don't have a.
Can you repeat? I didn't get the last part.
I'll just start over. So when you have a leader, someone can just propose, here's what I want all of us to agree on. Then you start the consensus mechanism.
Okay.
Without a leader, you have to go through an n-squared communication complexity of seeing what you want to try to agree on first.
Can you explain why it's n-squared versus n?
You need every node to talk to every other node without a leader. When you have a leader, that gives a good way to for someone to. So if you have imagine a set of n nodes, right? And say one of them is the leader. That one can just say, "Here's what I want all of us to agree on." And then you start the communication process, and that's that initial proposal is and a complexity. You're telling every node one thing.
Yeah.
If you don't have a leader, then you have to have all of these nodes come to a consensus, and by all of them talking to each other. That's an n-squared communication complexity because every node talks to every other node.
So there's n nodes, they have to talk to n other nodes, so there's n-squared communication complexity.
Yeah, they have to find out what everyone else knows.
Yeah, but we fall into the same situation when if the leader is Byzantine, right? In that case, that's why the third round. That's why there are two rounds, like pre-vote and pre-commit, rather than just one round, because there's a possibility of leader going Byzantine. So eventually we pay, like, because there's a possibility of leader being Byzantine, we had one more round of a ON square round, right? So how does having a leader really help?
I don't think there's ON squared when in the optimistic case. You're right that the hardest part about PBFT is when you have like a Byzantine leader or you have some kind of like some other kind of problem, some other kind of like liveness failure. You go into a very complicated O of N squared like view change system. But in the optimistic case, you're doing O of N.
Okay, so you're saying it's in the worst case, it's same as the without a leader thing, but if it's in the more optimistic case, it becomes better. Is that the main idea?
In PBFT, you still have N squared even for like the optimistic case. Reliable broadcast essentially needs N squared communication. You can the proposer still needs to tell everyone what his value, and then everyone tells everyone else what their value is.
Yeah,
that's still N squared communication.
Yeah, but then okay, so then I guess what is the benefit of having a leader then?
Yeah, that was my initial question.
Oh, it's about like how you need a way to figure out what everyone else knows. You can't if you want to where do you get the value that everyone's agreeing upon? So if you don't have one person proposing the value, then just to get the proposal of the value, you need like you can kind of look at what like Honey Badger does, right? What Honey Badger does is it requires this like round where everyone is sort of talking to each other about like, here's everything I know, what's everything you know, and then we kind of create a like this like what's the word they use? ACF, what's the word again? Something common subset. Accountable common subset. I don't know, something about like they need a way to figure out what is the subset of all the stuff that everyone, or at least enough of us have access to that data. So that way we can actually start to like commit it. The whole point of the proposer, the leader system, is it's a efficient way to make sure everyone has the data that we're agreeing on. So we're not just agreeing on stuff and then like we don't have the data later.
So also with Tendermint, like later on, it makes sense reading after Tendermint. You can use what Hotstep does to basically reduce this to an O of N communication complexity. I was kind of assuming that, but that's not true in what we're currently doing.
Okay. Like, do you understand what I mean here? Where like, how do you need a way for everyone to know? So let's say we're in a blockchain style system, right? We're trying to decide whether a block is valid or not, right? Everyone needs to know what is the block that we're deciding on so they can actually like, see is it a valid block or not, right? And if you don't, a leader system is just a way for everyone. So it's the efficient way for one person creates the block and tells everyone else the block, and that way now everyone knows. Okay, this is sort of here's the value. We're all agreeing yes or no on this. Otherwise, it's like everyone has their own mempools. It's hard. How do we know what we're agreeing on? What Honey Badger kind of does is everyone gossips about their mempool, and then we kind of figure out, okay, what's the subset of stuff that everyone actually knows about, and then
so I got that part. I was just wondering if there's no leader, we just add one more step of O(n) square, right? So the complexity is still order n square. So rather than being 3n square, it's maybe 4n square. So we are not losing that much actually, right?
So n squared, if using does not, it's n log n.
Also, what you're talking about is you're right, but also so one of the things that Tendermint also does is we were not the data the values that we're committing on are large pieces of data, right? These are like big blocks. Like let's say Bitcoin cachers, right? And, we're agreeing on 1 terabyte blocks here, right? So it's like, you don't want 1 terabyte blocks to be going through n squared. What you want is one proposer can be proposing these 1 terabyte blocks to everyone, and then everyone else is the actual last 2 rounds, pre-vote round and the pre-commit round. They're just gossiping about the hash of that entire data set, and they're agreeing on that. And so the amount of data that's going over the gossip network in the n squared rounds is a very small piece of data.
That's fair.
So yeah, that's kind of one of the main things. That also, in the Tendermint system, Tendermint was designed for this system in which we have a blockchain. So these are large values that are being.
PPF did the same thing.
Right.
Oh, got it. Thanks a lot.
Sure. There's a timer that just popped up saying remaining meeting time is 10 minutes.
Yeah, we can extend that if you want. How long do you think you need?
Okay, we'll go fast. All right. Okay, then the other thing is, so back to what I was talking about, the proposer selection is we want to, unlike PPFT, which has a single proposer until he goes down, we want a system that, rotates the proposer every round. So that solves 2 problems. One, it's like, we don't have this complicated system. It's like we use the, PPFT has the good path and the bad path, good times, bad times. What Tendermint does is says every round, in good times, we're always like constantly changing the proposer. And this also helps from a blockchain standpoint because we really care about censorship resistance. And if you have a system in which one person remains the leader forever until he gets kicked out, booted out, or goes down or something, whatever, he can censor blocks all he wants. While if you're constantly changing the leader in this like round robin system, basically every validator can censor blocks, but only in his time that he's the proposer, and it gives everyone equal chance to censor, and hopefully at least one guy is not being mean and isn't or at least really a third of the people aren't being mean and aren't censoring and stuff. But
I guess quick question on that.
Yeah.
If you have a re-election ever so often, or every round, then isn't that a lot of overhead rather than only when there's malicious behavior?
No, there's no overhead here. Everyone knows who the next proposer is going to be as part of the block. We can construct. Suppose there's no weighting since right? We can make an index of all the validator set. And you just iterate the height n, it's validator n. At height n plus 1, it's going to be validator n plus 1.
But if you use a round robin deterministic algorithm, aren't there other problems with it? For example, if you know the proposer ahead of time, you can DOS them.
That's not true in a gossip network. You can easily deploy up new sentry nodes and stuff. I can go through a long conversation why it's not true, but okay, suppose this is a huge concern. We can use this VVF and solve the same problem. It's not a big deal.
Validators can go through Tor. You can have sentry nodes. There's a lot of from an operational standpoint. There's
but then it puts the responsibility on the validators.
Yeah, exactly. And you make it such that they get punished economically.
So then someone has to write very good validator software so that everyone in the world can be validators if they want to.
Yeah, actually,
it's also not that hard. You need to deploy one sentry, right? Then now you have to go through a ton of network analysis to figure out who the validator's IP is. And you have to go through a ton of network analysis to figure out who the sentry for the validator is. Then you have to go hack the sentry, find the IP's connection of persistent peer, and then get into that DOS that validating backend.
But basically, my grandma can't be a validator.
Yeah, they can. You just run two sentries and two different.
Your grandma probably shouldn't be being a validator because part of being a validator is being able to have a hyper-secure, constant hot key. And in the case where your grandma wants to be a validator, I'm not so much worried about her liveness situation as her ability to create a node that actually has the security requirements in order to not get hacked.
Fair enough.
So the other thing is, like, in Tendermint, we have this current, like, deterministic round robin, but this is actually, and it's like weighted. Honestly, I think this is one of my favorite pieces of Tendermint that, like, is, like, super, like, undervalued, where we have this, like, cool system where it's like a non-choking round robin that's based on weight, and so you get to be a proposer in like relation to how much weight you have. But another thing is, in Tendermint you can easily add in a randomness beacon. Like, there's no, like, so Tendermint is designed as a piece of software that like is really good at doing consensus, and all of the, like, fanciness of, like, how who the validator set is, whether it's decided by proof of stake, proof of authority, blah blah blah. That can be passed in from the application, and it's completely feasible that we can pass in some, we can, in the ABCI is this, like, interface that we have on Tendermint Core, where you can basically run any state machine on deterministic state machine on the application, and you can use Tendermint Core to make it a distributed Byzantine fault tolerant state machine. You can add something to the ABCI interface where the application can pass in a random value, and then you can, Tendermint can just, like, shuffle the proposer based off of that random value. This is something that's not overly difficult to add in later on if we deem it necessary and the community thinks it's actually useful. Yeah.
Screen. Cool. Okay, I'm going to walk through a little bit about, like, the actual Tendermint consensus protocol. Can everyone see this screen that I have up here?
Yeah.
Okay, sweet. So this is a diagram from Ethan Buckman, who is or Bucky for short, the CTO of Tendermint. This is from his master's thesis from 2 years ago, 2016. And so this is, up until very recently, this is the best spec that we had for Tendermint consensus, essentially, other than the code itself. Recently, we had a new spec just last week that was just published. But that's, like, a much more academic, technical spec. It doesn't have these nice, pretty pictures and colors and stuff. So I think, for, like, brief explanation, we can talk a little bit about this. And then I'll talk about a couple of the main differences that went into the new spec that was just recently published. Okay, so essentially, to understand Tendermint consensus, you need to understand this diagram, and then these two paragraphs of locking conditions. Like, if you understand those two things, like, you understand Tendermint consensus. It's that simple. So essentially, what happens in Tendermint consensus is we come in and someone makes so one person from the round robin system they're the proposer, and they essentially have to propose a block. All the other validators have this timeout that they're waiting, where it's like, this is the timeout that you wait for a proposal. If in that
the same, does everyone have the same timeout?
Everyone starts with the same timeout, yeah.
Okay. How do they agree on the timeout time and, like, the new time?
That's in the protocol.
So there's some synchrony of a sort.
This is for partial synchrony. Well,
it assumes like a valid protocol, and part of the valid protocol is everyone starting with this timeout, and if everyone starts, like, distributing the code is inherently a synchronous thing.
No, I mean, no, that's not what I'm saying. I'm saying that if everyone has the same exact, like, are you assuming, like, globally synchronized clocks? Are you assuming that same timeout will happen at the exact same time?
In a singular round, yes.
Okay.
And then what happens is, after a timeout, whenever, like, next time happens, you increase the timeout, like, window.
So if you, I'll get to this. So let's assume that in a singular round, everything is synchronous, right? Let's assume this round is in like a GST system where, like, everyone has all communication is synchronous at this point, right?
Okay, sounds good.
So here, if someone receives the block in the timeout time, they pre-vote like yes to the block, and that means they submit a signature saying pre-vote, and it includes, like we talked about, just the hash of that block. And that's basically them saying like, yes, I have received this block and it is a good block. Then on the other hand, if they don't receive the block in time, or it's they get the block and it's an invalid block. By the way, one interesting thing, maybe if we have time, we can go at later in the end. Weird but cool thing that Tendermint does is it doesn't actually run blocks until after they're committed. So you might actually commit a block that has like silly, like bogus transactions in it, but that's okay. And we'll talk about why later. But yeah, so you pre-vote if you don't receive something in time. You do this like special type of vote. It's called like pre-voting nil, which is basically saying like, no, you know what, I vote against this. I haven't seen anything this round. I'm voting no. I'm like veto, basically. And so here you get into the system where you sit around and wait for the pre-votes from plus 2/3 of the other voters. And so let's say you have like less than 67% of the less than 67% of the voters online. Everyone sort of is stalled in this situation, and because it's a partially synchronous, we're assuming partial synchrony. At some point, everyone's pre-votes will get to you, whether they're a nil pre-vote or a block pre-vote. At some point, they will get to you, and once you do that, plus a little bit of timeout again. After every step, we almost have like a little bit of timeout. Where you vote for a little bit, you got plus 2/3, but now maybe you want to wait an extra half a second, see if you get something a little bit extra. Here, after that, you kind of now you decide, okay, if you have seen 2/3 of the pre-votes for the block.
For reference, the same block you had in case Poser sends multiple valid blocks.
Mm-hmm. Right. So if you, the one that you pre-voted on, if you see 2/3 pre-votes for the same thing that you pre-voted on, then you do something called a pre-commit for a block. And so pre-commit is basically saying like, okay, I have seen 2/3 of other people agree having seen this block. I'm going to create something called a pre-commit, and this is like kind of the more real vote. Like, I am committing on this block. Like I'm going to lock on this. I'll talk about what locks are. If you don't, you do this pre-commit nil. So let's say you see 2/3, but plus 2/3 plus 1, but like let's say a third of them were like pre-voting nil, and a third of them were pre-votes for the block, and you don't receive anything else. That means in this case you actually pre-commit nil, and what you wait for 2/3 of pre-commit. Now you get into another. You wait until you get 2/3 of pre-commit. You do a little bit of an extra timeout, and then you say, okay, did I see 2/3 of pre-commit for this block? If so, I commit. That means at some point everyone else will also see this situation, and it's safe to commit this block and actually start executing these transactions. If not, you go to and then you start the consensus, and with a new round at a new height. So now we're on block 10. Now we're on block 11. Now, if you don't see 2/3 pre-commit for the same block, now that means, okay, we didn't commit yet. We go on to this next round. So same height. We're still now on height 10 again, but now we're in round 2.
So this new round, is that like pre-vote nil and pre-commit nil are both messages, right? That nodes can send.
Mm-hmm.
Is a new round like a message, or is that just assumption of a timeout?
No, it's just something that happens internally in a validator's internal state machine that they say, we're going on to the new round. If they're the proposer, they propose the block. If they're not the proposer, they start their timer for the proposing timeout, like where they're waiting for a proposal to come in.
There is no timeout on pre-commits. That's an important part of this.
You mean after you receive 2/3 pre-commit?
No, there's no timeout for like waiting until.
Right. Okay.
Like you have to receive 2/3 of the pre-commits before you.
So what happens if you never receive those, right? Like it's not partially synchronous. Imagine just 2/3 people never reply after the pre-vote.
So when everyone comes back online, they would all have had a timeout or some issue on the pre-vote section, so that then their pre-commit would be nil. So that they pre-vote nil to everybody else. Once they receive a sufficient number of those pre-votes, they'd pre-commit nil.
No, I'm saying let's say you don't get 2/3 of the of people voting in the pre-commit step. Will it just stay there forever?
Yes. That's what these like stop sign points are, where it's like these are points where the protocol will like halt and like stand still until at least 2/3 of people come back online.
This gives us safety and asynchrony. So if the internet went down for like a week or something, Tendermint consensus would still be fine.
Yeah.
And it prevents people from being on like different rounds at the same time. It's like you can't just have like some people like on round 8 while some people are still sitting around on round 2 because all their clocks are like completely different.
Yeah.
It makes sure that everyone. What?
So it's highly consistency favoring.
Oh, absolutely, yeah. The entire premise of Tendermint was like, we said that blockchains are fundamentally useful for solving double spend problems, and double spend problems, like, the whole point is you're aiming for some level of safety. You don't want a situation where you have split brain. And so Tendermint was specifically designed that we always favor safety over liveness in an asynchronous system, and also that our goal is to make this is more like from the software side, but like and from the spec side, protocol side, but it's like we want things to be fault attributable. So we don't want just fault tolerant. We want it such that when there are nodes that are acting Byzantine, we can usually like recognize their Byzantine behavior and punish them in protocol in the application state machine for acting in that way.
So I like to add one more thing. On something Zubin said earlier about this being partially synchronous and you're relying on clocks being synced. So we do actually account for clock drift. Well, we have the system like BFT time. That's a time based in this fault attributable like manner that's Byzantine fault tolerant. And then so everyone syncs their clocks that new on-chain time to prevent drift.
Sounds good.
So basically, essentially, what happens is every time you go to a new round from in the same height, all of the timeouts become slightly longer. So now, and essentially, what happens is, let's say given a certain timeout, things look asynchronous. But now, let's say in the next round, the timeouts increase, and now at some point you might have to go through a couple of rounds. At some point, you will always get to a round where all messages arrive within timeout time, and so therefore everything looks synchronous at this point. Yep.
Yeah. So you said that it's only partial asynchrony assumption, right? So in that case, you don't know the time bound. You know that there is some timeout, but you don't know the time bound, right? Mm-hmm. So in that case, how do you set the timeout period? Because
so what we do is this is in like the configuration of how the protocol is set up. But so it's in asynchrony, it's perfectly safe, and then it needs partial synchrony to go on to at some point the timeout keeps increasing, and currently I believe in the protocol it increases by 250 milliseconds every round.
So the timeout increase is linear.
Yeah.
Okay.
Does that answer your
So
question?
you just set a number and then you like increase it linearly. Like there's no logic behind how do you set that timeout. Is that correct? It's just empirical.
You want to minimize this to avoid ever going into another round, but you also want to keep it small so in case a poser is bad, you get to the next round quickly.
Yeah.
There's a trade-off that you get just by experimentation.
Yeah, I think it'll be really cool. Like, I don't think anyone's really done any like particular like testing in like a real distributed system to see like what is the optimum starting timeout and what is the optimum like increase, right? Like maybe for example, when we have our global system with like 50 like sorry, not 50 like hundreds of validators around the globe, maybe starting at an initial timeout of 250 milliseconds is silly because at minimum like and every single time we always end up getting to the third round. And so like really all latencies are 750 milliseconds. In that case, then we can have like a proposal to like, okay, everyone reset your initial starting time at 750 milliseconds, so we're not going through wasting 2 rounds for no reason.
Yeah.
Okay, got it.
Yeah.
Another thing is like this doesn't have to be linear. It could be super linear. This time would increase.
Yeah.
Sounds cool.
Yep. Okay. So honestly, if you understood all that, you understand the diagram. Now the only
more detail than we needed to.
Yeah. Now the only thing that you need here is understand these 2 paragraphs. Okay.
Wait, just before we go on, is there anyone that has any questions about like the diagram at all? Anything like from like the network model to the synchrony model, like the anything? Okay. Awesome.
Cool. Yeah, Ethan's diagrams are on point.
Yeah, this is a really good diagram.
Yeah.
It's awesome.
Okay, these 2 paragraphs, essentially I'll explain them. It's called pre-vote the lock and unlock on pokeout. Okay, what does that mean? What that means is if you pre-commit on a block at some point, at some round, you are in this situation where it's called you are locked on this block. And what that means is when you are locked on this block, it is now Byzantine behavior to propose anything other than the block that you are locked on, or to pre-vote anything other than the block that you are locked on. If you see the proposal if you're not the proposer and you see the proposer and it's like not the block that you're locked on, you pre-vote nil. Dan Robinson and I have some like qualms with this. We think we can make it more efficient, but that's outside of the scope of this. In the current implementation of Tendermint, when you propose, if the proposer is proposing something other than what you're locked on, you're supposed to pre-vote nil.
Yeah.
If they propose what you are locked on, you pre-vote it. If it's your turn to propose, you propose it, the block that you're locked on. And you then sort of everything else runs the same way.
I want to backtrack 1 second. There's one cool thing when you're locked on something. That means that you have proof that at least F other correct nodes also agree with you.
What is F?
Oh, sorry. 1/3. 1/3 other nodes agree with that are like honest agree with you. There's like this fundamental rule of Byzantine systems where like you have to assume that the number of Byzantine nodes is less than 1/3. The other 2/3 can have like some like partial synchrony differences and stuff, right? But that only 1/3 can be actively malicious. So when you were locked on something, that means you saw like 2/3 other people on it. So only one of those thirds could be malicious. The other 1/3 had to have been correct. So we know like when you're locked on something, it's like 1/3 of other correct like no validators agree with you. That's just one of the cool things about locks. Sorry.
And then when you see 2/3 of people pre-committing on something, then you know that at least 1/3 of people see another one. Wait, does that make sense?
Yeah. When you pre-commit on something, like 1/3, 1/3 of rather correct processes like agree with you.
Mm-hmm. Okay, great. So if you get into this situation, then the only rule about locking is you have to propose and pre-vote. That's a rule. All the whole pre-commit logic works the same way and whatnot. But now we get into a situation where imagine we have some like synchrony situations where some people, let's say one guy saw 2/3 plus 1 people pre-vote for a block, block A. He sees all their pre-votes. He pre-commits on A. He's locked on A, but no one else actually saw the 2F plus 1, the 2/3 plus 1 pre-votes for A. So no one else pre-commits on A. Only this guy has pre-committed on A. Now it's like everyone goes to the next round, and the new proposer, he proposes B. And everyone else, 2/3 plus 1, see that, they all pre-vote B. a bunch of people pre-commit A, pre-commit B, and now you get into a situation where you might get into a liveness issue where you need 2/3 plus 1 to commit a block. You might have like a third of the honest nodes pre-committed on A. That's not enough to actually commit A because you need 2/3 plus 1. You might have like 2/3. You might have 1/3 plus 1 pre-committed on B. They're all locked on B. That's not enough committed because you need 2/3 plus 1. And then the last 1/3 are Byzantine. They say we're not signing ever, and so now you have a liveness issue where it's like, okay, everyone's locked on. Half of the honest nodes are locked on one block, a previous block. Half of the honest nodes are locked on another block, and the other people are Byzantine, so they're not helping at all. So in this case, now we are in a liveness issue. We've broken liveness. We can't terminate. Now this is where the rule about unlocking on a polka comes in. Polka is, you might think it's like, oh, some like fancy term from like traditional consensus literature, and no, Bucky just like, I don't know, he saw this diagram or something and he thought it looks like the Polish polka dance and he called it a polka. And now there's a blockchain called Polkadot for this reason. It's like this whole thing. Yeah, it's awesome. Yeah, so he calls it a polka when you see 2/3 plus 1 people pre-vote on something. So, maybe I should have brought up this term a little bit earlier. You pre-commit on something when you see a polka on a certain block. You see 2/3 plus 1 pre-vote on that block in the same round. That's a polka. So we have a rule where if you are locked on something and you see a polka for a higher round, you are allowed to unlock. Because that essentially means that, look, there are enough people who are not locked on the same thing you're locked on, and that means there are people who are locking on something higher now, and it's completely feasible that that might get committed, and so it doesn't make sense for you to be stuck locked on something because then you get into a liveness issue. So what the paper here says is that when you see a polka, this allows validators to unlock if they pre-committed something the rest of the network doesn't want to commit, thereby protecting liveness, but it does so in a way that does not compromise safety by only allowing unlocking if there's a polka in a round that the validator has become locked. So this allows you to say, oh, I saw a polka, okay, I'm going to unlock, and now I'll go, I'm free, I don't have any more locks, I'm done. This had some weird bugs in it, a live lock bug, where, this is a very complicated bug to find, but essentially, there's a case where a Byzantine actors, given if you unlock, they can do fun network partitions and stuff, and they can schedule messages in such a way that they can perpetually break liveness if they wanted to. And so this is where one of our consensus researchers, Zarko Milosevic, he proposed a solution where, this kind of seems almost obvious in retrospect, but it's if you see a polka, you don't just unlock from the lock, from what you're already unlocked on, but you rather only are allowed, you can relock on the new thing. So if you use a polka if you're locked on A, in the old system, if you see a polka for B, you're allowed to unlock and just now you can go propose C if you wanted to. And this just gets into the situation where you might just never do anything. But in the new system, this is one of the main things that's presented in the paper, is if you are locked on A, you see a polka for B, you just relock on B, and now you join the coalition that's gonna hopefully commit B at some point. This kind of seems almost obvious in retrospect, but I guess yeah.
This is found in kind of a cool way. It's a couple of people so Zarko found this just being a wizard, and then there were a couple other people independently who were trying to formally verify Tendermint, and they just came across the same issue.
Yeah. So that's kind of cool. That honestly, I would say that's probably the biggest difference in the paper. One new benefit in the additional thing that's in the paper that you can't really actually see in this spec here. It's not really a spec; it's more of like a layman's explanation. But something that was definitely a bug in the code that was fixed in the spec and now is fixed in the code, or at least there's a PR that's open and about to be merged soon, fixed in the code, is there's also this weird situation where in the code what was happening is if you pre-voted nil, no, sorry, what was it? Okay. If your clock is a little bit off of everyone else's or something. Oh no, sorry, that has nothing to do with clocks. It's, let's say the proposal is much larger. If you see 2/3 plus 1, and you're still in the proposal timeout time, if you see 2/3 plus 1 people's pre-votes on something, and you haven't seen that proposal yet, we had it such that you automatically pre-voted nil because you're like, oh, okay, I haven't seen this block yet. I'm just going to pre-vote nil and start my pre-vote timer. This actually can get into a weird bug where there's a situation where imagine some people have just faster connections than you do to the proposer for some reason, right? You can get into a situation where 1/3 plus 1 people saw the block and pre-voted for the block. Let's use the terms of F, right? F plus 1 people saw the block and pre-voted for the block. F people are Byzantine and pre-voted nil. The last 1/3, they got that F plus 1 voting for the block, F voting nil. They got that, and they see, oh, okay, I see 2F plus 1. I better pre-vote nil now. And then, because now you have 2F people pre-voting nil, no one's gonna be able to pre-commit in this round. And in theory, an attacker with this like weird network situation could actually perpetually delay, cause a termination issue where you never actually terminate.
This would actually be fine if you were pre-voting nil after automatically seeing 2/3 pre-votes on saying approve on the same block hash, which is I think there's just like some.
Well, the main thing that was done now is that you don't automatically vote as soon as you see a block. As soon as you don't automatically pre-vote nil as soon as you see the 2/3 plus 1. You actually do mandatorily have to wait till the end of your proposal timeout, and then you pre-vote nil, and then we kick ourselves back into like a safe partial synchronous situation. I'm sure that was kind of complicated and may have been like, sorry about that. But I was told to talk about what's new in the paper, and that was kind of like one of like the key big differences that was in this paper, and another liveness bug that we killed. Yeah. Does anyone have any questions at all on Tendermint consensus, on Tendermint Core? Tendermint Core is this like piece of software. It's like probably it is a piece of software written in Golang, and it does Tendermint consensus over some arbitrary state. It literally does not care what's being passed in as long as the state is deterministic, like transitions. And the cool thing is you can write blockchain applications on top of it in basically any language you want. You can write it in Go, JavaScript for some reason, Rust.
It's always doing it in Java.
Java, yeah. You can write blockchain applications, anything. You can literally turn any state machine that you have into a deterministic Byzantine fault-tolerant machine. And we had a test net. Even today, actually, it's still up, I hope. I haven't checked this morning yet. But it has, I believe, 112 validators. It is probably the largest distributed BFT consensus instance that has ever existed in a distributed in a public distributed setting. So if you want to be part of that, you can get some stake and join the testnet. Stake is our coin that we're using. The term like STEAK, like the meat. That's the name of the coin. Zubin would like that.
I
and,
would like that. I do like that.
Yeah, you can join and run a validator. And yeah, largest EFT public blockchain, public consensus system.
How's the performance are you guys anticipating?
So the problem is performance can be hard to define, right? Because like we can talk
latency, throughput.
Also, it's computation.
Sorry?
The bottleneck is always computation. So
Yeah.
it's, and you have to price the computation correctly.
Mm.
No, our benchmark
and network, like the proposal broadcast.
Oh, my bad. Whoops.
Well, it's both. It depends on it depends on your state machine, right? In some state machines, like in Bitcoin, they like all the transactions are relatively simplistic, and so therefore the bandwidth is more of an issue. But in Ethereum, for example, you can create a very computationally heavy transaction in a very small amount of space. So the computation is more demanding. It really depends on the application.
Yeah.
In general, the proof of stake does give way better throughput than the proof of counterpart.
Right.
If it's not a computationally bounded system.
Right. Oh, another thing that maybe that's worth pointing out is, okay, why safety and asynchrony is so important. Like why you would prefer safety in that situation over liveness or okay. In a synchronous protocol, right, like proof of work or many of the proof of stake systems out there right now, there is a situation if you have your block time and you have your network latencies.
Yeah.
If your network latencies ever exceed your block time, you go split brain and you wouldn't even know, or it'd be very hard to know. So let's say the amount of time needed to propagate blocks in Bitcoin was over 10 minutes. It took 11 minutes to propagate blocks. So the problem is no one could get their blocks out to everyone, because at that time someone else would find a block, and there'll be blocks all over the place, forks for days. That'd be bad. So that's why Bitcoin does this absurdly high block time at 10 minutes. Ethereum lowers it to 15 seconds using some magic with Ghost Protocol, but it's kind of questionable whether that I don't know if it actually provides the same security guarantees than what Bitcoin does.
Instant finality makes it such a double spend can't happen in these forks.
Well, so I'm not talking about instant finality here. So the part I really want to talk about though is an asynchronous system. You can try to make block times as low as possible. We can say, let's try to have half a second block time. And if our network latencies don't fit in half a second, if it's greater than half a second, then it's oh, oops, okay, we didn't come to consensus this round. Okay, let's just increase it next time. And so, then hopefully next time when it's 1 second, now, oh, great, okay, now we can do it in there. The cool thing about an asynchronous system is you can try to push the block time as low as possible without the fear of if it accidentally goes too low, it's a catastrophic the world blew up situation.
And in the optimistic case where everyone's live and the pros are being good, we are operating at the network latency plus computation time.
Yeah. So on our current testnet, we purposefully set so between the commit stage and the new proposal stage, we purposefully set I think 5 second timeout. So that's the time where after you receive 2/3 plus 1 pre-commits, you wait an extra. Now you start waiting your timeout to see if you can receive any more pre-commits in that time, and that's when you actually are executing your block. I don't know why we were just
it's solely to limit the amount of space you have to store on a testnet.
Yeah.
People are using Oz instances and pay for every byte of memory.
Right, and so we don't want blocks happening every second. We just said, okay, let's have blocks happening every 5 seconds, so that way, there's a fifth of the number of blocks in this week. And then, so really, I think our actual block times are about 6.1 seconds right now. So the 5 seconds is in this, I don't know if you can see my mouse or not, but it's in this, after the pre-commit time. So that means the rest of the cycle is taking about 1.1 seconds.
Yeah.
There's a site, Some community members made like this site, Pigment.network, Cosmos.
Wait,
Yeah, it wasn't
oh,
us.
that's so impressive.
Right? So yeah, they made this thing where it's like, I think this is probably like the best like block explorer. Like it's honestly better than the one that like Tendermint made so far. You can see all like the cool, a lot of the stuff of like the validators. Like you can see what each validator's voting power is. How did he get 750? Okay, whatever. What their uptime is, and then here you can see some stuff about like this is the current block we're on. 90% of the voting power voted on the last block. The average block time is 5.85 seconds. So that means like I said, we have a five purposeful 5-second timeout, and that means the rest of the voting time is taking 0.85 seconds on average over the last 100 blocks.
I see Dave and JL Andrews and some other people.
Yeah.
This is their Sunny node?
Oh yeah.
Yeah.
Where's the Sunny node?
Sunny node is right here.
Ah.
Yeah. I don't think Zaki knows that was me. So. Good. No, I prefer to not know. People not know. But yeah, I don't know why like the block time has slowly actually been going down over time. This is probably because more nodes are coming online, and as more nodes come online, the block time is actually decreasing a little bit because you need to wait for 2/3 plus 1. So in our last testnet, we were actually in this like funny situation where like we had basically exactly like 67% of the nodes online, and it's like right at that edge. And so basically, out of the people who are actually online, you need to hear from everyone in that synchrony in a round in order for you to actually commit the block. And the probability of hearing, if you have more people, if you have 90% of the people online, there's a higher likelihood of you hearing from at least 67% of them within one round. So as the amount of people online as the voting power has increased, the block time has also decreased slightly.
Yeah.
What's up?
Yes.
I
You're muted.
can't hear you.
No, hey, you're muted.
Muted.
You're muted.
You're the third from the top. This is your name.
Oh, sorry.
Panay, nice to meet you.
Yeah.
Okay.
So in these testers, do you also simulate Byzantine nodes, or are like all these nodes fair and acting in the best interest of the network?
These are public entities that we have no control over. Whether, for all we know, they're acting Byzantine. I don't know. We did have some Byzantine nodes in like previous testnets, not purposefully Byzantine, but people who just like run the wrong software, and so that counted as Byzantine essentially.
So I'm just wondering, like, are there any nodes which are actively attacking each other, or like because the average block time is failing here, like slow getting down here? That means like everything is happening smoothly. That's what.
Do you want to create some scripts to like attack the network? We would love that. We need more like battle testing.
So we have an adversarial testnet planned, and like I have a couple of scripts. I just haven't been deploying them just because it's like I don't know. It seems kind of boring to deploy.
We have like this testnet is a relatively collaborative one. We have one that's coming soon called the Game of Stakes, where what it is all the validators, the Interchain Foundation, which is sort of the foundation that kind of what's the word for it? Created Cosmos, and like did the fundraising and stuff. They are running a competition called Game of Stakes, where we'll have a distributed testnet. And the validators who maintain the best uptime actually get a gift of atoms from the Interchain Foundation. So it's kind of nice where like a lot of the validators, such as me, for example, did not buy into the Cosmos fundraiser and don't have any atoms right now, but maybe want to be validators at launch. So the Interchain Foundation will sort of like if you participate in this Game of Stakes and you do a good job at maintaining uptime,
and you're not an employee,
and you're not an employee of Tendermint, so basically in this Game of Stakes, we highly encourage validators trying to like hack each other essentially.
Also, you get like rewards for finding vulnerabilities in our code base. Like we use a custom encoding scheme. If you can get a RC from there, that would be legendary.
Like, got it.
Yeah. So yeah, essentially we're having a testnet where like but this is, to be fair though, that testnet is more about like trying to attack the liveness of other validators, so trying to like DDoS each other, so we can like force everyone to harden their security on that aspect. Regarding testing whether the network's resilience is Byzantine fault tolerant, like to double signing actors and whatnot, it doesn't make sense that anyone would do that on the game of stakes on purpose, because then they'd lose the game of stakes, because hopefully we detect that. But like I said, we in a previous testnet we actually did have a situation where someone ran old software by accident and then updated to the new software, and for some weird reasons. And our evidence reactor, which is sort of what Tendermint uses to gossip evidence of like Byzantine behavior, we did catch the evidence and people did get slashed and whatnot.
Yeah, we've been having double signs.
We've had double signed, mostly for accidental reasons on people's part, but the system has been good at catching them.
So while me and Sunny are still here together, does anyone have any questions about like some research things that we've been working on? That's probably one of the things we don't have too easily accessible on GitHub at the moment.
Right.
Because we've been focusing on like coding all this stuff up so we can launch and start building those things.
One of like our main interests post launch are like I think from the researchy standpoint, like the next step that we're trying to take Tendermint towards is using aggregate signatures at the gossip layer to aggregate votes to reduce the communication overhead and hopefully reduce block times, allow for a much higher number of validators. With a good gossip network layout, you should be able to like reduce it from n squared messages needed to n log n. And so, hopefully we can go from being able to support hundreds of validators to, maybe 1,000 validators. I don't know, Dave, you can probably speak more to the.
I don't know if people are interested. Like we have gone pretty over time.
Yeah.
So you guys ask questions here, then we can answer it. Okay, so people are interested. So,
any research plans for application level sharding?
Yeah. So, okay. So, we talked a lot about what Tendermint does. The Cosmos project is sort of a stepping into interchain communication. So, we have this belief that like, sharding is this like nice thing, and people are working on very fancy, like theoretical, how would we do this and whatnot. How we see this whole step towards sharding is like it's a very sequential, incremental system. And the first thing that we're trying to do is just do basic interchain communication, where let's have two chains that are light clients of each other and can send tokens amongst each other. Two separate, completely independent chains that don't know anything about that are run by separate validator sets. But they know about each other using this protocol that we have called IBC, or inter-blockchain communication. And then, once we have this IBC, once we can have the point where we have like a solid, this is essentially side chains, right? Once we have solid side chains, then we'll start working on stuff around how do we get the validator set of one chain to be the same as the validator set of the other chain. So, how do we communicate validator set changes and slashing Byzantine behavior evidence over IBC? That's kind of what you need for that. Then you start doing stuff into, okay, what if we don't need the whole validator set validating that chain, but you want a subset of that validator set validating that chain? That gets into more of the sharding kind of stuff. And so, yeah, we do plan to explore this stuff. But, honestly, we need basic interchain communication first.
So, also to your original question, also for the record, you're muted. You're showing a green light, so it looks like you're trying to talk. But we are, what's it called? The idea is like for crypto, say you have CryptoKitties, right? Or Augur. You'd go build your own, you'd deploy your own blockchain with your validator set or something, and then you wouldn't have to fight for throughput or gas or anyone else.
So this increases this is advantageous for you and the whole system. Advantageous for your users because they pay less gas. Advantageous because you don't have to fight for throughput here, but you can still connect with full security.
Question there. So if I'm making my own blockchain with my own application running on top of it, I have to find my own validator set?
That is the hard part of this, yes.
Yeah, for now. Like I said, right now we're focusing on sovereign zones. And I think, honestly, all these ICOs and stuff that are happening, the best use thing for to put these tokens to use is probably to use them as proof of staking tokens on a blockchain. But yes, in the future, then we'll start working on how to, for example, the Cosmos Hub, which is the main blockchain we're working on, how can that validator set offer its services for validating other chains? And hopefully our goal is that the Cosmos Hub should be the most secure proof of stake blockchain in the world. And so the idea is then how can they take that security and lease it out to other chains, essentially, if that makes sense.
Yeah.
Gotcha.
Sounds good.
So another
when's mainnet slated for?
Q4 2017.
That's it's not that far away.
Yeah.
Months away.
But I don't know. We don't make official. After we failed to miss our deadline twice, we stopped making official claims about when our launch is. But I'll just say that we've been cranking away all summer in Berkeley, California.
There's been tons of code outputted.
Yes, lots of code, lots of commits, lots of bugs in live test nets, which is fun.
There's now a randomized testing framework for our blockchains.
But yeah, honestly, a few months. Honestly, it shouldn't be too much more than that. And then, we have.
That's not big.
Yeah, a few months. Honestly, a lot of the complexity that we're working on is the Tendermint side of things is actually very fleshed out. Essentially, it's pretty solid. It's going through official auditing and whatnot.
Yeah.
The main thing where most of our bugs are actually popping up now and is actually around the staking logic, which is not in Tendermint, it's in the application. And so one of the things that we're really focusing on is our system uses a concept of delegation where you may have coins but don't want to run a validator yourself. So what you can do is you can actually delegate your stake to a validator, and he validates on your behalf, and you get back the earnings, but then the validator can charge commission.
And all the unbonding and redelegation of stake is handled in the application state machine itself, not as a separate add-on on top.
Right, and we've been adding some cool features around redelegation. So one of the things that I think that Rizal and I kind of did, which was very important, was we allowed this concept of redelegation, where in most proof of stake systems with some concept of delegation, let's say I as a delegated to validator A, and then I don't like him anymore. I want to delegate to validator B because validator A is just he's been having liveness issues and whatnot. So let's go. I want to switch. But to switch, I have to unbond from that validator, which can take, in our case, 3 weeks. But, I know Ethereum has been thinking of 6 months. Then I have to go through this period with no reward and then rebond. And that adds such a stickiness factor to the validator set. And so we wanted this ability for people, in proof of work, as a miner, I can jump between mining pools super fast. We wanted to add a similar characteristic to the relationship between delegators and validators, where if I don't like you as a validator anymore, I can instantly redelegate to another validator. And so this logic has been honestly the biggest cause of bugs, is it's actually a very complex system, especially if you want to make it hyper efficient. Because so in our model, we assume 100 validators, but we're assuming, a large number of delegators, let's say hundreds of thousands or something, right? And so we're designing our system in a way where how do we make sure in every block, for example, we don't have to iterate over 100,000 delegators because we're not going to do anything else in that block. We're going to spend all of our computational time just doing the reward distribution and whatnot. So I guess this is going a little bit away from the Tendermint side of things, which is what we were supposed to talk to, and more into like the Cosmos proof of stake. Tendermint was, but a little bit teaser into maybe a future episode. I don't know. But yeah, the nice thing about Tendermint, you can use it with anything you want. You can use it as proof of work if you want. You can use it.
Tendermint? No, use that.
Why? You just submit proof of work to the state, and the state accumulates.
Oh, that could be your statement. My bad. I thought that was a consensus.
Right. Not Nakamoto proof of work, like proof of work as Sybil resistance. Yeah.
Thank you so much, guys. Like, really appreciate that. That was awesome. Any questions? If not,
Yeah, you can find them on Telegram or Twitter.
yeah, that was like super cool. You guys are frozen now, I think. Oh no, you're not. You weren't frozen. You were just like. Well, that was an awesome explanation. It's like exciting to see Cosmos, such an exciting project. Yeah,
we
thanks.
didn't even get into Cosmos. That was all Tendermint, man.
Yeah, well, Tendermint, Cosmos,
the whole other world.
The exciting.
Everything is just really ambitious and like really exciting.
You mean a whole nother universe, right?
Yeah. Okay.
Yeah.
Bye.
Peace.
Are we all supposed to sign off now? Is that what's happening?
You want to?